Hi, this last part of the tutorial to introduce the singular value decomposition to you is crucial in really gaining an understanding of what the SVD is trying to tell you. Okay, so beyond mathematics, how do you get some intuition for what the SVD is? Now, this is the way I like to think about it. The SVD provides you the best approximations. Okay, let me make that a little clearer. The best rank 1 approximation of A in operator norm is given by D1 U1 V1 transpose, right? So let's parse that a little slowly. Remember that if A is an M cross N matrix, right, whose SVD is U D V transpose, then the UI is an M cross 1 vector. The Vi transpose is a 1 cross N vector. And so UI Vi transpose is an M cross N matrix. D1 is just a scalar which multiplies this M cross N matrix. And I'm claiming that out of all the rank 1 matrices that exist, the one with the lowest operator norm error, right? So if I minimize over all B which are rank 1 with rank 1 and I take A minus B operator norm, then the minimizer is going to be exactly D1 U1 V1 transpose. Okay, so let's go a little slower and get a little more intuition of what's going on. Now, when I write down A as UDV transpose, this D is a diagonal matrix. Okay, so just imagine its entries are 5, 0.3 and 0.1. Well, what it's really trying to tell you is that when I add these, so remember the additive form of the SVD, which is the sum of I is equal to 1 to R of DI UI VI transpose, right? So this was the other form of writing the SVD. Well, it's saying that U1 V1 transpose has a coefficient of 5, U2 V2 transpose has a coefficient of just 0.3, and U3 V3 transpose has a coefficient of just 0.1. So if I was to take a rank 1 approximation of A, that is, ask for the rank 1 matrix which best approximates A in the operator norm, my best bet is to just take D1 U1 V1 transpose. That's what this says. So I haven't proven this fact to you, right? I have not proven this, but you'll have to take it from me that you cannot do any better than taking D1 U1 V1 transpose, right? So in some sense, the first singular vectors and the first singular value, that captures the maximum energy of the matrix. Most of the matrix is given by D1 U1 V1 transpose, at least when it's in this fashion. So if the second singular vector was 4.9, then well, the first two singular values and vectors are both equally good, right? So that's fine, and then we can write a similar statement in that case. In that case, we can say that the best rank 2 approximation, so if I'm allowing to choose from all matrices which are at most rank 2, then the best rank 2 approximation of A in operator norm would be given by D1 U1 V1 transpose plus D2 U2 V2 transpose, right? So there's basically that's, I mean, if you wanted the best rank 2 approximation, take the first two terms of the SVD in this summation. That's really important. So it's like saying that I can, if for example a lot of the entries are small, then I can just set them equal to 0 and I won't lose much. The resulting matrix will still be close to my original matrix in operator norm. Great. Okay, but well, what about other norms? For example, what about the Frobenius norm, right? But it turns out that exactly the same theorem holds for the Frobenius norm as well, right? So let me state it again, just so that you hear different ways of saying the same statement. Given a rank R matrix A, right, the rank 1 matrix that is closest to A in Frobenius norm is D1, U1, V1 transpose. So that is, out of all the rank 1 matrices that you could think of, right, the one that's closest to A as measured in the Frobenius norm is exactly given by the SVD. Okay, and here the approximation error in both cases can be calculated by A, the original matrix, minus my approximation of A. Okay, so that's the error, and I can measure that in either operator norm or Frobenius norm. When I measure it in operator norm, from this summation, if I remove the first term, then I'm just left with the sum over from I equal to 2 to R of di ui vi transpose, in which case the operator norm of that sum is just d2. And similarly, if A is just written as this summation and I remove the first term, then the Frobenius norm of what remains is just the sum of I equal to 2 to R, so that should be R, of di squared. So that's the approximation error in both cases. And again, as I was saying, that if d2 is small, the second singular value is small, or in some sense the sum of squares of all these other singular values is small, then I can gain a lot by just dropping all of them and setting them to 0 and keeping only the first entry. Of course, there's no reason that I should only be looking for rank 1 approximations, but as I said in the other case, and I'll say it again over here, the best rank K approximation to A in the operator or Frobenius norm is exactly given by the first K terms of the SVD. And this is true for all K up to, from 1 till R. So, this is really crucial in understanding the SVD. If you were to write down the SVD of your matrix and you found that, apart from the first 3, which are really large singular values, the other singular values are small, then that means that you can set those other singular values to 0. You can ignore those other elements in the summation and you won't lose much. You'll only lose an amount that's really small. If all the di squares were small from from 2 to R or from some other K to R, if those singular values were small, then the error that you get in approximating A by a smaller matrix, by not smaller in size, this is also M cross N, but in some sense it's a much simpler matrix. It's a smaller rank matrix. It has a smaller dimension in some sense, and that's what one will often do in dimensionality reduction. Is you're given a more complicated matrix A, but then when you take the SVD of the matrix A, maybe A has 10,000 dimensions, but maybe the first singular value is 100, the next one's 10, maybe the next one's 1, and then it becomes exponentially smaller after that. Well, what this way of understanding the SVD is telling you is that if I just threw away all those smaller entries, that is, I just set them all to be equal to 0, and I calculated the resulting matrix again by just multiplying U, D, V transpose with D having these smaller elements set to 0, then that is going to be a very good approximation to A. So in some sense, the SVD tells you what is the best way to approximate your original matrix. I think that's the most important way in which you can remember what the SVD does. It tells you what are the basis directions which have the most energy. So remember that these U1, V1 transpose, U2, V2 transpose, and so on, these are basis elements for A. Why are they a basis? In fact, they're an orthonormal basis. Well, they're clearly orthogonal to each other because U1, V1 transpose, if I take the dot product with U2, V2 transpose, right, by the dot product is given exactly by the trace of the A transpose B, so that's V1 U1 transpose U2 V2 transpose, and you know that U1 transpose U2 is 0. That was That's how the U's were formed. They were orthogonal to each other. So this is 0. So these are two m cross n matrices that are orthogonal to each other. Not only are they orthogonal to each other, but you can also convince yourself that u1 v1 transpose, when I take the dot product with itself, so with u1 v1 transpose, I just get 1. So these matrices actually form an orthonormal basis for the matrix A. So it's a specific basis for A in which to decompose A. And what the SVD is telling you is how important each of these basis elements are. So it's telling you that the first U1 V1 transpose is the most important with a weight of D1. U2 V2 transpose is less important, has a weight of D2, and so on. That wraps up my introduction to the SVD. And I'm sure that at some later point you'll want to return to this to revise how to think about the SVD. And I think this is one of the best ways to think about it, as providing good approximations to your matrix.